Hey guys, I want to give you a quick overview of a couple of the main parts of the structure that I've developed. Um, so let's just get right into it, and then hopefully I explain and get you uh, up to speed on this. So I am doing this as an overview for the guys on my team, but I'm hoping to be able to share this and hopefully uh, spur some thoughts and whatnot for other teams as well. So here we go. Um, we start off with just our subsystems. So basically, each subsystem has itself and states that that subsystem can be in. Obviously, robot still runs everything, whether it's an autonomous or teleop. Robot container still gets all of the user inputs from the controllers. Um, Sequences, autons are just special sequences. So sequences are things that we run during teleop that control and tell the subsystems what they need to do, similar to commands, except they are state-based, so they are step-by-step inside of those. It makes it really nice and clean and easy, and that's the whole point of state-based. So autons, and these are basically the same type of deal. There's some extra stuff that an auton is that these other sequences aren't, and that just really comes down to these root classes that are built that these all extend and implement. So um, to start off with something really simple, if we look at robot really quick for state base, just like everybody else, we have our robot init function, and in here we create a couple of sensors and such that are used among multiple subsystems. So we have to create them here. Otherwise, we create them in the subsystem themselves. Uh, first got rid of robot maps, so did we. And we just put them right into the subsystem that they belong to. We're going to skip some of the path planner and auton chooser stuff that's available. You can go and look at it on our GitHub. Um, so in autonomous periodic and in teleop periodic, we have a quick loop here. This is based off of our designated loop period. So while it's autonomous, if current time minus previous time is longer than 20 milliseconds, you can see here that's 20 milliseconds. We move along. Um, and I am going to put this into presentation mode just so everybody can see this better. All right. And then obviously in here, if you're running autonomous, sometimes you want to have a delay. So that's what we're looking at, and then you can process it afterwards. Not so much focusing on the actual code of this, just walking through the logic, and I want you to see how easy it is to like think through it. And yes, there's code, but the thought process there is way more important, and then you can write code that follows this thought process. So your you have your auton basically set up and tell the subsystems to be in a certain state, and then the subsystems know that based off of their subsystem state what to do with the hardware. And then in teleop, same thing, except instead of an autonomous, you're looking at the controller inputs and calling individual sequences, and those individual sequences tell each subsystem to be in certain states, and then they control the hardware. So it's like an extra level or a step in there. Um, so this is where everything really does happen. Is it's in like 5 lines of code, but then it like goes all the way down and runs everything. So if we look at, say, for teleop with the sequence processor, okay, um, we have we we have a bunch of let me get in here. So we have all of our sequences, and then we initialize them. We tell them what the neutral state is, and then the start state. Each sequence runs through a set of steps, right? States. We need to tell it what neutral is. All of them are neutral. When it's in neutral, nothing's happening. It's dead, basically. You know, a button hasn't been pushed, whatever. But the start state is the first state that it goes to. If you do press that button, it starts there, and then there's logic to switch it to other states if need be, depending on what you've written in that sequence. So, and then there's logic for starting them. And this is like really, this is like the most important part. This is where a lot of the, uh, this isn't magic. This is like, you got to really think about it. It's quite difficult sometimes to get all the buttons and the logic right. This past year, we had a climb for 2022 that was basically autonomous. It was autonomous as long as they were holding a button. Once it grabbed onto the mid bar, it would windmill up to the high bar. Then it would recenter itself, let go of the mid bar, go up to the traversal bar, recenter itself, drop the high bar, and end up on the traversal bar. And it was using limit switches for doing that. So, but when we initially started it up, we actually had to have a two-part sequence. So one part was actually just moving the arm up so it would hit the bar and it would touch it and the sensors be able to see the bar. But as soon as it saw that, then we could have the climb button could be pressed, and we made sure that the previous sequence was in prep for climb. We just named the sequence that, so that once it was up and touching the sensors, it would go into this state, and then we would do a double check on the sensors. Ours were pull down sensors, so it's not always the best way to wire them, but it's what we did. I highly advise doing pull up sensors just in case they come unplugged, because if they come unplugged, then that acts as a signal that they're touching, so you don't want that. Anyways, so ours were pull down. So, and then it would start it. Now in here, this is just some overrides, but the logic of it is when we want climb to start, we want it to take over the other state that was requiring it, the prep state that was bringing it up, or the prep sequence that was bringing it up. And also, you're currently driving. We wanted to override that and say, no more driving. We want to control the states inside of the climb sequence. You know, so there's a lot more to this. And then once you get all of them started, you want to loop through and process them. Now, if they're in neutral, they're not going to do anything. It's not going to do anything. But if they're not in neutral, based off of the state, it'll set the it'll make sure that the subsystems are in their right states, and then once all these decisions have been made, back here you'll have back here, once all your decisions for your subsystems have been made by all of the different sequences, then your subsystems run. So they already know what they need to do based off the state, and they just go. And it makes it super nice for programming purposes. Let's just hop over to Auton. I know I'm going through this really quick, but it's the best way that I know how to do it, just so everybody can kind of get a broad overview of this. And it's recorded, so you can go back and, maybe I'm not getting everything, but so for Auton, you would have a chosen Auton from your schedulable chooser, and your sendable chooser is something that you put on the dashboard, and you can choose an option, and it just has text that you put next to it. So These were based off of position and what you wanted to do from that position. So we just had a couple of positions on the field, and we could do different things based off of that. But they were assigned with an enum to an aton. This aton enum kind of bundled together a path with some other information, um, and so we've got several of them here. We had to set the path planner followers from the file. This is kind of very specific to us, but for instance, with Auton options, we would do this. Each one of these options is a new instance of an Auton sequence. So we would make this available in here, and we would just set the path planner followers after because we want to load the path planner information from the files inside of robot.init. We were getting issues if we did it um, in the enum itself. So like in here, so we didn't do that. So Auton, you choose the Auton in the sendable chooser, and then it runs during autonomous. So when that runs, I'm just going to choose one of them. And I gotta, for instance, one ball Auton. Um, so one ball Auton has neutral, drive, shoot ball, punch, and reset punch. So basically, it would drive the robot from its starting position, and then it would shoot the ball. It wasn't actually shooting the ball because we had a little punch that would load it into the shooter. So the once the shooter was up to speed, then we would punch the ball and it would actually launch. And then we would do a final like reset the punch because we'd punch it up and then we need to get it back down. So you can see in here that during drive we wanted swerve drive to drive autonomously, and we want our shooter to start getting up to speed. And then we have another set here for shoot ball. This is up to speed, and then here we would shooter state punch. So this is all in autonomous. We tell it exactly what to do, and then in order to switch states, the logic is down here. So drive, you set your path planner follower. Um, you have to do this so that the drive train knows what it needs to be following, and the swerve drive subsystem can do that. There's a lot going on in the background here, and then once that path planner follower is done, it goes on to shoot the ball, and once it's crossed 1,000 second or 1,000 milliseconds, so 1 second, and the closed loop error on our shooter is low enough, so it's close enough to what we want it to be as far as RPMs go, then we'll go on to punch it. We'll punch, we'll wait a half a second, and then it'll go to reset punch, and then we'll wait a half a second, and then we'll go to neutral. So then it's ready for us to go when we get to teleop. So very, very nice, simple and easy and very effective. And as those are going, you know, we're going to be running our subsystems as they go. So swerve drive actually has a very simple process. This is actually in the base drive subsystem. So if you were writing your own, if you had this base drive subsystem class, you wouldn't have to write anything year over year for the most part. We're still working on building up this base class, but it updates the odometry and then it goes in. It checks if it's still required by a sequence, sees if the state has changed, and then that creates a flag for like first loop in the new state. You can use that in your code. Um, and then check to turn off is something for solenoids I was trying to build in, but uh, it grabs the state, the subsystem state, and processes whatever you told it. Well, how does it know what it needs to do in that state? So each one has has a, let's see, hold on. Huh. I guess I just have to, I gotta exit. Okay. Sorry, I lost track there. Um, so for swerve drive, for instance, you have to have your swerve drive state. And this is where every time you tell the subsystem to process, it grabs onto its current state that you've set from the sequences, whether it be auton or teleup, and it follows whatever state. So, like in autonomous, you saw the drive autonomously state. When the swerve drive subsystem is set to drive autonomously, um, the subsystem is passed into a lambda function, and it knows that it's a swerve drive uh, subsystem that's passed in. So you can do the swerve drive subsystem, get state first run through. We would normally do like a check to make sure that your point for your start odometry is close enough to your current point, so you don't mess things up. Because sometimes you don't trust yourself, and you could cause a runaway robot, right? If your point is like 1,000 feet away, all of a sudden your robot's gonna start going crazy, um, and well, just driving straight towards that point, and you don't really want that. So, if your path state controller is not equal to null, so it's got something to follow, then drive along the path that it has. Otherwise, you haven't set the path. Given error, you're not gonna like how I have the error there, but it is what it is. Um, yeah, so this is a very new structure. It's just something I came up with, um, but it makes programming very simple. I was able to go over this with my students, and hopefully they can be more and more independent, even with a more complex robot. Um, it is very hard to give students the ability to do this independently when we don't have like a strong FTC program or anything like that. So students come into FRC knowing very little other than some of the uh, programming courses in school, which we all know aren't super duper useful. I guess it all depends on what the teachers teach in those classes. It's not to say that they're useless. It's just not. They don't always come in with the knowledge gain and the knowledge of the first libraries and such that you need. So, um, this would allow them to be more independent, so we could focus on other things, focus on vision, focus on bringing in sensor stuff for the robot instead of spending all of your time actually trying to figure out how to get the basic functionality of the robot going. We need to get beyond that. It seems like every year teams still struggle to do this, and I'd like to be able to make it possible for teams not to worry about programming. It's a goal of mine. I've helped way too many teams, and so have many people in first. So I'm hoping that this code helps, and I am going to stop there. We are at 20 minutes, so have a good day.